Welcome to Maths with EJD. In this video, I'll be talking about some special cases and common pitfalls of binomial series. There are actually three aspects of this particular title, but I'll be taking the first part in this case. So talking about special cases, and common pitfalls, right? Common pitfalls. So the first situation is where I'll be talking about the expansion of 1 minus x raised to power n. 1 minus x raised to power n. That's one special situation we need to pay attention to. Then we'll also be talking about common errors, common pitfalls and misconceptions, right? Common pitfalls and misconceptions of binomial series, that is, misconceptions. Then lastly, we'll be talking about tricks for quickly tricks for quick calculations, tricks for quickly calculating, for quickly calculating, calculating binomial coefficients, binomial coefficients. Okay, so that's what this next three videos will be about. But the first one is to expand 1 minus x raised to power n using binomial theorem. So let's go for that right now. Okay. Yeah, expansion, or expansion using the binomial theorem. That's expansion of 1 minus x raised to power n. That's what this is about. So we can say that the binomial theorem states for this specific situation where we have 1 minus x raised to power n, so we can say that's a summation from k equals 0 to n of of n combination k. Now, normally we know this should be 1 raised to power n, x raised to power 0, and that goes on. But all the 1 raised to power whatever is going to just be 1. So at the end of the day, all that would matter will be the signs. So we can say this is just minus 1 raised to power k, x raised to power k, instead of explicitly saying 1 raised to power k, 1 raised to power n minus k. All the 1 raised to power n minus k. In fact, let me even demonstrate that so that that can be really clear. So what we should really be doing is 1 raised to power n minus k, then minus x raised to power k. All right. So, but you know that all of this 1 raised by n minus k is going to be 1 in the long run. So this is going to be summation from k equals 0 to n, then n combination k, then you have minus x raised to power k. So which you can actually break down to summation from k equals 0 to n combination k. So here now you can see this is like minus 1 times x raised to power k. So um this can simplify to summation from k equals 0 to n combination k, then minus 1 raised to power k, then x raised to power k, x raised to power k. So that is what 1 minus x raised to power n is going to be at the end of the day. Now, this is important because this minus sign is really crucial, because as the values of k changes, as k takes 0 or even values, you are going to have a positive sign, but as it takes odd values, you're going to have negative signs, and that is really important to pay attention to. All right, so let's of course you'll still remember that n this n combination k is the same thing as n factorial over k factorial n minus k factorial. Okay, so now let's look at some special cases of this situation. Special cases. Okay, so the first one is where n is equal to 0. So that means you have 1 minus x raised power 0. And anything raised power 0 is 1 without stress. So we see that this result holds for any value, of x due to the zero exponent rule, due to the zero exponent rule. Okay, now the second special case would be where n is equal to 1. So when n is 1, you have 1 minus x raised power 1. And anything raised power 1 remains the same. So this is just 1 minus x. So when you raise anything to power 1, it remains just what it is, basically. So next, we have another, let's consider where n is equal to 2. So when n is equal to 2, right, you have 1 minus x raised to power 2. In this case, this would be, this will actually be only 3 terms, right? This will be, this will simply be 1 minus 2x plus x squared, which all of that is 3 times. So which expands, by now you should notice that whatever the power is, whatever n is, the number of terms you are going to have is going to be that power plus 1. So now we have power 2. So you have 3 terms. When the power was 1, you had 2 terms. When the power was 0, you had 1 term. Okay, so this expands to 3 terms, as you see, 2 combination 0, 2 combination 1, 2 combination 2. These are the things you're going to have. So actually, all this determine the coefficient. This determine the coefficients. Okay. Then we have special cases where we have negative powers, right? So let's go for such situations. Imagine a case where you have negative and or fractional powers, right? Negative or fractional powers. So either of them, that means you have n is less than 0, or n is less than 0, or n is non-integer. N is non-integer, meaning n is a fraction, right? So in that case, I mean, for such cases, for such cases, for such cases, the expansion becomes infinite. The expansion becomes infinite. Okay. And it is such that you have 1 minus x raised to power n, and that would be equal to, of course, you already know how this goes already. So using the formula, okay, well, let's even use the formula we have deployed here. So that's summation from k equals 0 to n, right? I mean, well, it's actually, okay, we don't even have to worry about that. Let's just go. Okay, the power is infinite here, so we just have to follow what we have, right? So the number 1 raised power n minus x raised power 0 divided by 0 factorial and all that. We've done that quite a number of times. So all of that is going to become 1 minus nx plus n into n minus 1, uh, all over 2 factorial. Then, of course, x squared is what you have with that. Then next you have minus n into n minus 1 into n minus 2. Then this divided by 3 factorial. Then you have x raised to power 3. And the terms continue like that. So here, this is valid. This is valid only for absolute value of x less than 1. And I've said it a couple of times. The absolute value of x less than 1 means you have minus 1 less than x, then all of that less than 1. So if it falls with outside of that range, then the rule doesn't hold anymore. The expansion becomes infinite and it converges. So in essence, what we are saying here is that the expansion, the expansion becomes infinite. Okay, it becomes infinite and converges only for absolute value of x less than 1. So that's exactly what that is about. So, and just like I said, when you have cases where you don't have that is not negative or fractional, right? Um, so I can make this as a kind of comment up here, right? That you can take note of that for positive or maybe it can still come after, right? So this is fractional. So I'm just making a claim outside of this totally. So we say that for um for positive for positive integer n, the expansion the expansion the expansion has n plus 1 terms. Okay, so this is a kind of special case when you're expanding 1 minus x raised to power n. So we just need to pay attention to this basic stuff. Very simple, but worthy of attention. Okay, and that is the essence. And we've seen that the simplification, just like we've seen in all of these places, like how this came about, that we now have this. So based on the expansion from k equals 0 to n of n combination k, then we have minus 1 raised to power k, x raised minus 1 raised to power k, yeah, x raised to power k also. All right. So when k is 0, when k is 0, we know that's when we have 1. When k is 1, we have this negative sign, minus 1 raised by 1, that's negative. And then n combination 2, another will give us 2. And you have x raised by 1 right there. So when it's 2, when k is 2, 2 combination 2 will be 1 also. That's why the coefficient of x squared is 1. And then minus 1 raised by 2 is positive. That's why this is positive. And then you have x raised by 2. That's exactly why we have this. So you can also apply that idea here. So we come to the end of this video for a special case for binomial series. So if you have not subscribed to this channel, please be sure to do that right away. And of course, hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how these videos are helpful to you. And if there are assignments or some practice questions, let me see feel free to supply the answers in the comment section. And of course, let me know if you have a topic you like me to teach or a problem to solve, and like and share so that more people can have access to this great content. So like come your way again, keep doing maths right. Bye.